It's a great honor for me to introduce Robert C. Martin, colloquially called Uncle Bob. He has been a programmer since 1970, and he's most recognized for developing numerous software design principles and for being a founder of the influential Agile Manifesto. Mr. Martin has published dozens of articles in various trade journals and is a regular speaker at international conferences and trade shows. He is also the creator of the acclaimed educational video series cleancoders.com. Mr. Martin has authored and edited many books, including the following: Clean Code, The Clean Coder, Clean Architecture, and Clean Agile. A leader in the industry of software development, Mr. Martin served 3 years as the editor-in-chief of the C++ Report magazine, and he served as the first chairman of the Agile Alliance. Please help me welcome Robert C. Martin. Robert, the stage is yours.
Well, thank you very much. And it's a pleasure to be here virtually anyway. It's a country I've wanted to visit many times, but not had the opportunity. Maybe next year. In this case, however, let us proceed. We're going to be talking a little bit about architecture. Architecture, the lost years. Now, let's see if this next slide button works. How about that? This technology is unbelievable. So many years ago now, my son, Micah, who is a software developer, showed me a project that he was working on. And what you see on the screen is a picture of the directory structure of that project. And if you are familiar with Ruby on Rails, it's easily recognizable as a Ruby on Rails project. You can see that by the names of the directories and the structure of the directories. And as I looked through it, I recognized it as a Ruby on Rails project. And then something occurred to me, something that hadn't occurred to me for several years. Why is it that the very first thing I see when I look at that directory structure is Ruby on Rails? Why don't I see what this project is? What is this project doing? Why do I see the framework up front and I don't see the purpose of the project up front? And so that made me think. Ruby on Rails is a web framework. It's all about giving us access to the web. And the web, of course, is an I/O device. It's a delivery mechanism. It's an I/O device. It's something on the outside. The web is not part of our internal data processing. It's a peripheral. Why is it that the very first thing I see when I look at the architecture of this program is the I/O device that it uses? There's something wrong with that. So I started thinking about architecture in general, and I started looking at the blueprints of buildings, the architectural diagrams of buildings, and I noticed something. Look at this blueprint. Look at this diagram here. That's a library. You can tell that it's a library by looking at it. You can see the bookshelves and the tables with computers on them, and there's something called a circulation desk there. And okay, maybe that one doesn't convince you. Well, then this one will. That's a church. Notice how the shape of the building, notice how the architecture screams at you about the intent of the building. It's not telling you that it's made of bricks and wood and metal. It's telling you what the building is for. And that started stirring something in my mind. Architecture is always about intent. The architecture of a building is about the intent of the building. So that made me remember this guy. His name is Ivar Jakobsen. Ivar Jakobsen wrote a book in 1992 I see the book right on the screen, Object-Oriented Software Engineering, a use case-driven approach. And he described architecture to us way back in 1992 in terms of use cases. What is a use case? Well, a use case looks like this. And by the way, the term use case was very popular in the early 90s, and then it became much less popular because all the consultants rushed in and destroyed the concept by trying to differentiate it over and over and over again. And later on, we changed the name to user story so that we could have a word that we could use that was not tainted with all the consultants. Well, that failed too, but never mind. This is a use case in the manner of Ivar Jakobsen, and it's a very simple idea. You take a requirement of the system and you phrase it in terms of the data going in, the processing steps that need to be executed, and the data coming out. And you can see up here, this is the create order use case, and it has some data going in, like the customer ID and the shipment destination and the payment information. And there's some processing steps there. They're labeled 1, 2, 3, 4. The order clerk issues the create order command. The system validates the data. The system creates the order and determines the order ID, and so on. And it shows you some output data. The system delivers the order ID to the clerk. That's the output data. Now, notice that this use case does not describe anything in detail. It's a very high-level thing. I'm not talking about the internal data structures there or the very detailed processing steps. It's a high-level description of what this system is supposed to do. And a normal system would be composed of many hundreds of use cases like this. Or if you'd rather, you can call them user stories. Now, Jakobsen said, each use case can be turned into an object in the sense of a Java object or a C# object or a Python object, whatever language you happen to be using. A use case can be turned into an object because a use case takes in data, processes the data, and exports that data back out. I like to call these objects interactors. Jakobsen used to call them something else. Jakobsen used to call them controllers, but that is too close to a model view controller, which I don't want to talk about right now. So I like to use the word interactor. An interactor is an object that implements a use case, but it talks to another object that implements high-level business rules. We would call this kind of object an entity. Entities are independent of the application. An entity could exist in many different applications. An interactor, a use case, is particular to the application. So I call the interactors application specific. I call the entities application independent. They're both business rules, but they are different in level. Entities are high-level business rules. Interactors are lower-level business rules that have to do with the input and the output and the way a particular application works. Jakobsen also defined a third kind of object, which he called an interface object, and then later changed the name to boundary object. And I've denoted those here as interfaces, typical Java-style interfaces, C# interfaces, C++ pure abstract classes, however you want to, call them in your language. These are polymorphic interfaces that allow access to the interactor and allow the interactor access back out. And if you look carefully, you will notice that one of those boundaries is used. That's the top one there with that open arrowhead. And the one on the bottom has the closed arrowhead. That is implemented. That's that closed arrowhead there that looks like a pizza slice. That's an inheritance relationship or an implements relationship. So the interactor implements the output boundary, the input boundary. The interactor implements the input boundary. The interactor uses the output boundary. And we'll see why in just a minute, because that's a very important distinction. All right, so now we're going to take a look at how the system would work in this kind of Jakobson environment. Got a little user down there. That user is using some mechanism to talk to the system. Let's say that it is the web. Let's say that the mechanism he's using is a website. It doesn't matter, but let's say that it's a website. So the user fills out a form, let's say, on the web page, and then clicks the submit button. What happens? What happens? Well, the delivery mechanism, whatever code you've written in there, takes the data from the form and repackages it into a data structure called a request model. This request model is a pure data structure. It is not part of any framework. It is a regular old Java object or C# object with mostly primitive data types in it. I don't want any dependencies on other things inside the request model. It's just as simple a data structure as you can make. And then the delivery mechanism, the web in this case, passes that request model through the input boundary to the interactor. Now you can see why the interactor implemented that boundary. That's a polymorphic call. The delivery mechanism calls a function on the input boundary, and the interactor implements that function, taking in the request model. And what does it do with the request model? It begins a dance of the entities. I believe I hit that next slide button, but let's try it again. There we go. The request model goes into the interactor, and the interactor then starts to control the dance of the entities. One more slide I need. There it is, the dance of the entities. What's going on here is that the interactor is responsible for knowing how to deal with the input data and then what to do with the entities, the real business objects. And once it has used those real business objects, it then reverses the flow and begins to gather data from those entities, the result data of the operation, and put that data into another data structure. That data structure we call the result model. And again, this is just a plain old data structure, no dependencies on frameworks, just primitive, mostly primitive data types and, very application dependent kinds of data types in here. And then the interactor passes that result model through the output boundary back to the delivery mechanism, where the delivery mechanism will somehow display it to the user. Whether it's a website or a console or a thick client, doesn't matter. Now, can you test those interactors? You can, can't you? Do you need the website running in order to test those interactors? No, you don't, do you? No, because all you have to do is, in your test, is create a request model and pass it to the interactor, and then get the response model back and make sure it's the right response model. You don't need the web running at all, do you? No, this is a testable architecture. And by the way, any well-designed architecture is a testable architecture. Now, what about model view controller, you say? Aren't we supposed to be using model view controller? Well, let me tell you a little bit about model view controller. This is Trygve Renskog. I can't pronounce his name properly because I'm an American, and no American can say Trygve Renskog properly. However, this is the fellow who invented model view controller long, long ago in the late 70s. And when he invented it, it was a small little pattern which involved a model object, which was a nice little business rule, a controller object, which gathered input for the model, and a view object that took data from the model and displayed it somehow. And when I say it was a small pattern, I mean that anything on the screen, a button, a radio button, a checkbox, a text box, would have its own model view and controller, right? We did not have a model view controller for the whole screen. We had model view controllers for all the little itty bits on the screen. That was the intent of this pattern, which of course has gotten completely perverted over time, as most things do, because nowadays on web systems, you see this kind of pattern where the model objects are now called business objects, and the controllers are the things that talk to the web, and they gather data and they throw it at the business objects, and then the views take the data out of the business objects. And the problem with this notion is that there are no firm boundaries here. Very often we get controller-like code in the business objects and view-like code in the business objects and business object-y-like code in both the controllers and the views. There's a smearing of the intent. Now we go to the next slide, and I'm going to skip that slide. So let's go one more slide. And here I'm going to show you how we cross the boundary. And this is on the output side. So here the interactor has done its job. The interactor has created the response model. It passes the response model out through the output boundary. And now look what's implementing that output boundary. There's an object there called a presenter. The job of the presenter is to take that response model, which is a nice generic data structure, and turn it into something that can be displayed or something that can be output. The job of the presenter is to reorganize the data in the response model so that it can be easily presented. So, for example, the response model might contain a date. If it does, it is a date object. The presenter will take that date object and turn it into a string. In the view model, it will be a string. The response model might contain some kind of money in a currency object or a money object. The presenter will then convert that into a string. You kind of get the idea here, right? The view model is created by the presenter to produce a bunch of strings and maybe some flags in the appropriate format so that the view, which as you see I have drawn as a ghostly object with barely any implementation, the view has almost nothing to do. All it has to do is copy the strings. Maybe look at a few flags to turn some colors. Nothing much to do in the view. The view should be so simple that it does not need to have any automated tests. The presenter can be tested automatically because all you need to do is pass it a response model and look at the view model. So again, we have a testable architecture. Now, next slide, of course. What we see here is the output side of the entire system. This is the architecture from the interactor going back out towards the web or towards the delivery mechanism. And you can see the whole picture there. And the reason I've drawn this picture in this way is that I want to denote that double black line. You see that double black line? That's an architectural boundary. Architectural boundaries separate levels. The stuff on the left is low-level I/O code. The stuff on the right is high-level policy code. Now look at the direction of every dependency that crosses that double black line. And notice that every single dependency points towards the high-level policy. This is a fundamental rule of architecture. Low-level code depends on high-level code. High-level code never depends on low-level code. And what do we mean by the word depend? I mean source code dependencies. Lines in the source code that mention the name of other modules. Import statements, using statements, pound include statements, all those funny statements that we put at the top of our modules so that our compilers know what other modules we need. Those are the source code dependencies. And every one of those must point towards higher level stuff. This is the dependency rule. The dependency rule of clean architecture. Low-level things have source code dependencies on high-level things. High-level things never have source code dependencies on low-level things. And what does that mean? Well, take a look at the controller and presenter out there. Can you see that the controller and the presenter are a plug-in to the business rules? That you can plug the web into the business rules without the business rules knowing that there is a web out there? You can take the web and plug it in. And by the way, if you can plug it in, you can unplug it and you can put your test system in. You can plug your test system into the business rules and test your business rules. Or you could plug a console interface into the business rules. Or you could plug a service-oriented architecture interface into the business rules. And by the way, I should say that the word service-oriented and the word architecture do not go together. There's no such thing as a service-oriented architecture. Service orientation is a communications mechanism, not an architecture. Microservices are a communication and deployment mechanism, not an architecture. And let's see, let's go on another slide. Got a couple more we can do. Oh, what about the database? How does the database fit into all of this? Next slide. Well, you may have noticed that databases tend to be very important things in our applications. And you got to ask yourself, well, why are they so important? Because you know the database is really just an I/O device, right? The database is just a place where we store things. It's an I/O device. Why would we elevate it to such a high level in our systems? The databases are not high level. Databases are low level things. And what do we do with low level things? We put them on the backside of a boundary. Here's our interactors again. Our interactors are using entities. Our interactor is using an entity gateway, which is a polymorphic interface, which is implemented below the boundary by the entity gateway implementation, which uses the database. Nothing above that double black line knows that there is a database. It knows that there's an entity gateway. The entity gateway contains methods. Those methods allow access, but there's no SQL above that black line. Even the layout of the database schema is not known above that double black line. All that is known above the double black line are the entities. Do the entities come out of the database? Oh, they might. You might have Hibernate running. Maybe you've got some object relational mapper running. That's fine, but it's running below the black line. It's a low-level detail. I don't want anything above that architectural line to know anything about Hibernate or any of those other little details down there by the database. And what does all this mean? Notice that all the dependencies cross the architectural boundary, pointing towards the high level. The database is a plug-in to the business rules. And if you can plug the database into the business rules, you can unplug the database from the business rules and plug in something else, like a RAM-based database. You know, when you want your tests to run really fast, you don't need the real database down there. You can have a RAM-based database down there, or even a completely stubbed database that only returns fixed values. Because if you can unplug the database, you can plug anything you want in there. Now, with that, I believe I've exhausted my time for this talk. It was a 20-minute talk. I gave you the basics, went through all the important details. I will now entertain any questions you might have.
Okay, question time. So one thing I would like to ask you, because I was looking to your presentation and I was thinking that I always thought that a user story is a vertical slice. So it contains an interactor, an entity, a presenter, and so on, and a fragment from a database. So it's not just an interactor, it's not just a use case. And you make this, let's say, equivalence between use cases and user stories. Aren't user stories more than a use case, actually?
So in both cases, use cases and user stories are vertical slices, right? They go all the way from the input to the output. This architecture recognizes that the input and the output are details. They are I/O devices. And that although they are part of the user story, they must be separated by layer. So we look at the input side and we separate it out. We look at the processing steps, we separate them out. We look at the output side and we separate that out so that those three things can be independent of each other. Are user stories and use cases different? Only in their format. Jakobsen's idea of a use case was very strict input, processing, output. User stories over the years have become much less formal. They're more like little descriptions of behavior that we want to see, written in a few sentences. And then they become formalized with acceptance tests. If you're in an agile environment, you've separated the formality of the requirements so that the informal requirement is a user story and the formal requirement is the acceptance test.
Okay, thank you.
You're welcome.
I have another question for you. I was thinking to implementing a clean architecture. How could you enforce it? Is it easier to do it inside a software company than for, I don't know, for outsourcing projects done by community? Where is easier to enforce a clean architecture?
Well, the word enforce is probably not the word I would use. I don't, how do I say this properly? A good architecture is the creation of a team that has a unified vision. Everyone on the team understands what the architecture is and what the architectural principles are. And in that environment, there is no need for the notion of enforcement. There is always a need for someone to be the visionary, someone or maybe some small group of people to be the ones that set forth the vision that everyone else follows. That's very normal, right? But the vision of the architecture is shared by the whole team. It is difficult to do that in an outsourced environment. If you are a company and you want a software system created for you and you hire an external consultant and then you attempt to supply an architectural vision to them, you'll find that extremely difficult. If you're not in there working on it, it's very difficult to maintain the vision properly.
Okay, thank you. We have a very interesting question here from one of our participants. Mariana Vumvulea asked, what is the modern way to create clean architecture? Is there something new? Because she says, I see these concepts you shared are timeless.
They are timeless, that is correct. The definition of architecture, the principles of architecture, are as old as computing, perhaps 70 years old. These ideas have been around for many, many decades. And there is something about software that we all need to understand. For the last 70 years, we have ridden on top of a hardware technology that has gone crazy, right? The amount of advance in the hardware is stunning. The advance in software has been almost non-existent. We still use if statements, assignment statements, and while loops, just like we did in the 1960s, in the 1950s. We still do object orientation, created in 1966. We still do structured programming, created in 1968. We still, and barely have started using functional programming, invented in 1936. Our industry, software, is static. It just rides on top of this other industry, the hardware industry, that took us on an exponential ride for decades and has now stopped. We now live on the plateau, folks. It's going to be a nice, level time for the next several decades.
Thank you.
You're welcome.
Another question comes from Angelo Bueno. He said, nowadays everyone talks about microservices.
Yeah.
What is your brief opinion about it?
So my brief opinion about microservices is that they are vastly overrated and vastly overused. There's a reason to use microservices, and that reason happens to be things like scalability and failover and so on. But the reason that is often touted is encapsulation and organization and architecture. This is just dead wrong. Microservices do not give you a better architecture. Microservices are not a particularly good mechanism for encapsulation or decoupling. There are much better ways to encapsulate and decouple than microservices. Microservices are just another instance of a good idea that got way overblown and everybody tried to spin it and spin it and spin it. And, you know, another few years down the line and everyone will go, gee, I wonder why we did that.
Well, here goes another question from Tomasz Czobo Domokos. In our project, we have implemented everything using the components of the framework we are using. Where and how should we start separating our business rules?
Oh, well, that should have been done at the start. You don't want to take your business rules and tie them into your framework because, and by the way, that's what the framework authors tell you to do. The framework authors tell you to bind your business rules into my framework because my framework is so wonderful. Why wouldn't you want to bind yourself to me? But a good architect is very skeptical of frameworks. Not that you won't use them because they can be powerful and helpful, but you look at a framework with a very skeptical view. You think this framework is out to screw me. And so you back away from the framework, you put a layer between yourself and the framework, you use it, but you do not commit to it. Otherwise, that framework will rule you for the rest of that project. You want to look at a framework as something that you can decouple from if you need to. If there's a better framework that comes along, you will want to switch. You want to make sure you can switch. So you always keep the framework at a certain arm's length. If you have not done that, and now you live inside of a project that is tightly bound to the framework, it's going to be a very difficult time. The decoupling is going to take a long time. I would not make a project out of it. I would try and do it as slowly and carefully and iteratively as possible, behind the scenes, not making stories out of it, don't go to your boss and say, we need 3 months to decouple from the framework. That would be a very bad idea. Over maybe a period of a year or two, maybe the team can gradually decouple from the framework so that you're not quite so tied.
Here is another question related to Ruby on Rails from Sirius Tradichuk. He says, Rails may have a messy folder structure, but it helped many small companies build the first product fast and get on the market, like Twitter, Airbnb, GitHub, etc. What is more important, the project folder structure or the time to market?
Well, neither of those. The thing that's important is to do a good job. If you want to get to market fast, do a good job, right? That's the most important part of going quickly. The frameworks can help. You know, Ruby on Rails is a great way to start a project, but do a good job. Make sure that you're not tying yourself to that framework. It doesn't take much time or effort, and it will vastly speed up your development as you proceed. There is nothing more important for the speed of the project than to do a good job. Otherwise, you make a terrible mess that slows everybody down forever. And you've all experienced that mess, and you've all experienced the slowdown. Don't buy the argument that says, we have to make a mess so that we can get out in a hurry, because you never get out in a hurry when you make a mess.
Here is a very short one. It's software craftsmanship versus software architecture.
The difference?
Yeah, the versus, which is
the difference between software architecture and software craftsmanship. Software architecture is a high-level view, a high-level vision of the shape of the system. Software craftsmanship is the promise a programmer makes to do a good job.
Okay. Short question, short answer. Thank you. There is such a thing as clean architecture for machine learning. Can machine learning be integrated into clean architecture?
Well, I don't see why not. You can have modules that implement machine learning algorithms, and you can train them. There's no real reason that a machine learning entity could not be in an architecture like this. But I am very cautious about machine learning. I think machine learning is a good thing. I think the things that we've learned how to do with machine learning are very powerful and very interesting. But there is a trust developing that should not be there. These machine learning programs are not humans. They do not have human capability. They are not sentient. They cannot tell the difference between right and wrong. They are not ethical. They have no morals. They have no conscience. And we must not put them in situations that require morals, ethics, and conscience without human supervision. So, for example, I do not expect auto taxis anytime soon, because someone has to take responsibility for anything bad that happens when that auto taxi unfortunately does something awful.
The next one is about redesigning a monolith to service-based architecture. What approach and what technologies would you choose to do this?
Well, okay. First of all, you have to decide whether or not it's necessary to decouple a monolith into a service-based architecture. And be very careful about this. The times when it's necessary have to do with scaling and failover and the ability to use more than one server, say, up on the cloud or something like that. Now let us say that you have made that decision, that you have a monolith and you need it to be in a service architecture because you need scaling and throughput and so forth. Okay. Your first step is to decouple that monolith by normal means. And by that I mean you're going to decouple it without making services. Just decouple it into, let's say it's a Java project, decouple it into nicely decoupled jar files that have very well-defined communications pathways. And then if you need services after that, which by the way, you may not, but if you do, then those communications pathways, those function calls that go from one jar file to another, you can then turn those into service calls. Remember, every service interface is really a function call. And you want to model it that way. And you want your business rules to treat them that way. In fact, you want your business rules to not know that there is a service interface in the way of it, in between them. The service interface is an I/O device. It's a low-level concept, not a high-level concept.
There is another one regarding soft skills. What are the most important soft skills needed within a team of software architects to have a successful result?
Oh my goodness. All right. The most necessary soft skills are morals, ethics, conscience. The courage to do the best thing for your employer, even while your employer is fighting. Right? Sometimes you will get managers who will say, well, stop writing all those tests because it's taking too much time. And you must say, no, the tests are actually saving us time. The courage to stand up for your convictions is extremely, extremely important. It is also important to have a good set of standards and disciplines. What we don't want is a bunch of programmers who are doing whatever they want. They code any way they want to. They're just, I follow my rules, you follow your rules, they follow their rules. It's all different. We're all just free agents. No, that's not what we want. A good architect and a good team decides upon a set of disciplines and standards that they will uphold within their projects and within their efforts. We could go on with this. I mean, there are many other soft skills to learn. The soft skill of communication, the ability for two people to talk to each other. That's a really important skill. The soft skill of being able to talk to a manager. The managers have this skill already. You better get it too, because otherwise they will dominate you. And then they will win every argument if you cannot communicate back. So there's many soft skills that software developers need to learn. The ability to code is important. The ability to act as a human being on a project is also very important.
Nice. A longer one. Following design principles by the book frequently leads to over-engineered projects that become a nightmare to maintain. Do you think it's better to break these principles if it serves to simplify the code and make it better maintainable?
Of course, right? This is engineering. In engineering, you have a set of principles, and then you make a bunch of trade-offs. And sometimes the principles will lead you to what you consider to be over-engineering. And if you have thought that through and you can realize it well in your mind, then yes, of course, you say, well, I'm not following this principle because it's going to make my design too heavy. Now, be careful with this. Principles are principles for a reason. So a good engineer, a good architect does not abandon principles lightly. But I have never worked on a project which was perfectly principle-oriented. There are always trade-offs. In the end, software is a human endeavor, and human endeavors are typically a little messy inside. We want to limit that mess as much as possible, but we cannot eliminate it entirely.
Regarding that simplicity principle from Agile Manifesto, I've heard somebody saying that there is no such thing like reusable code. It's just reuse code, but this happens after you code it. So don't think that somebody will reuse your code. Just do it in the simplest way possible. How do you comment this?
Oh my! Well, the way that you create reusable code is to make sure that someone reuses it. So I completely agree with that. And by the way, that is extremely difficult. Having done it once or twice in my life, it is very difficult to create a significant framework that many people can reuse. Now, is it necessary to create frameworks that people can reuse? And sometimes it is. Sometimes it's a very good idea. Other times it's not. The effort required is very large. And very often you think, well, maybe it would be better if I just created something that was simpler and not reusable, and then that would save me a lot of effort. Mm-hmm. There's a lesson here. How do you make something simple? Mm-hmm. You make it as clean as possible. You do the best job you can. You try not to anticipate too many things. You don't put the hooks in. But you also want to preserve the ability to make changes, because software is all about making changes. So you want to be able to make changes. Therefore, you must not make the software rigid. So what is it that maintains the flexibility of software more than anything else? And that is a suite of tests. If you have a suite of tests that you trust with your life, you will not be afraid to change that code. What stops you from cleaning up code? What stops you from making changes to code? Fear. The fear that you will break it. But if you have a suite of tests, you will not fear that you will break it, and therefore you will clean it. You will make it better. It will come naturally because you will just run your tests. The tests have to run fast. They've got to be quick tests, and they've got to cover everything. But if you have a suite of tests that is very fast and covers everything, and you trust it with your life, then that project will be very easy to change. And because it's easy to change, you can make it very, very simple. You can take away all the complexities that you were hoping would make it flexible in the future.
Okay, thank you.
You're welcome.
Which is the most enjoyable project that you worked on and why?
Wow, what an interesting question. I've worked on so many projects and they were all, well, no, not all of them were enjoyable. I do have to say there were some I didn't like very much, but most of them were really enjoyable. Let's see, which one was the best? Long ago, I mean, 30, 40 years ago, I worked on a system where we had mini computers scattered around the country. And we would call them up on modem lines, 300 baud modem lines, and we would control them. And we would analyze and test telephone lines everywhere. We had this really lovely system. And it was all written in assembly language. It was all written in machine language on a machine that's very much like this one behind me here. You see this one over here? Yeah, this one with a little light blinking back and forth. That's a PDP-8. Actually, that's a Raspberry Pi which is running a PDP-8 emulator. But we had these little machines that were out there. They had, like 32K of RAM. And man, that was a great project to work on. I worked on that for years. I've also done a lot of really interesting work in like computational geometry. Imagine, for example, getting someone to draw the blueprint of a building on a graphical user interface, and then getting the files from that, and then analyzing it to see if it met architectural principles. For example, could you push a great big 48-inch beach ball through the entire corridor system that the architect designed? Those are really interesting mathematical and geometric problems, which I had a blast. I had a blast working on that stuff. I could go on like this. I've worked on a lot of systems that were really fun. I've worked on embedded real-time systems. I've worked on batch systems, financial systems. We've just worked on my career in software has been overwhelmingly rewarding. I've loved almost every second of it.
Well, another one says, I'm expecting in the next 10 or 20 years to be able to code in natural language. What are the last human skills that can be taken over by artificial intelligence?
You believe you will be able to code in a natural language. You know who codes in a natural language? Lawyers. That's what it'll look like if you're coding in a natural language. Because here's the thing about this, right? Programmers are detail managers. We have to deal with every nasty little detail. We're the guys who write the if statements that deal with the fact that text files sometimes end in \r, but sometimes end in \r/n. And, we have to write those icky little details about that. We're the ones who have to deal with the fact that, leap year has this really complicated algorithm to figure out. We're the guys that deal with the details. Why do we exist? Because the business people who hire us do not want to deal with those details. They give that to us. Now, you can say that we're going to be programming in a natural language. Fine, great. But it will be a natural language that can deal with detail. And that's what lawyers do. And so it'll be a formal language. It'll be an unambiguous language. It'll be an executable language. And you will still need programmers to write that language.
Okay.
Oh, gosh, this is fun.
Yeah, that's true. Which is the most difficult problem you encountered in all the projects you worked on in terms of architecture?
The most difficult problem I've worked on in terms of architecture. Wow. Well, I hesitate on this one because I'm trying to make sure that I'm not going to violate a non-disclosure. I don't think I will. Many years ago, say 20 years ago, I worked on a project that I had extremely high hopes for. I was just thrilled with this project. It was a graphical user interface for drawing software diagrams, and it just had so much promise. And I was not the architect on this one. I was a contracted programmer. And I believed in the architecture that they had put together. I thought it was a beautiful thing. Multiple levels and just gorgeousness. I thought, oh yes, they had an object-oriented database, and we were doing it all in C++. And I couldn't imagine a better approach. And it was a dismal failure. It was awful. It was vastly over-engineered. It took far too long to get anything done. The implementation was slow. The throughput was slow. Everything went wrong. All of our architectural goals failed. I learned a lot of lessons on that project about what are important architectural goals and what are not. Eventually, that product got thrown away, and the company bought a little tool that some fellas in Wisconsin had cobbled together in a few months.
How much time should you spend refactoring and improving existing code?
This is a trick question, all right, because the word time is not really useful here. How should you refactor? And here's how you refactor, right? You write a little test that fails. You write a little bit of code that passes that test, and then you refactor that code. And that entire cycle should take something like 2 minutes. Not much more. You can write a little test, it fails, write a little code, it passes, you refactor. Another test, code, refactor. Test, code, refactor. Yep, red, green, refactor, around and around that loop every 2 minutes or so. Now, if you do it that way, you don't even think about the amount of time you are refactoring. You just refactor. The word refactor must never appear on a schedule. You must never put on the schedule at the end, this is when we will refactor. This is always a failing strategy. It will lead to nightmares. Do not do that. Refactoring is something you do all the time. Every few minutes, you're constantly cleaning up the code. Does that mean that you don't sometimes have bigger refactorings to do? No, sometimes you do. And when you have bigger refactorings to do, the way you do them is to break them up into tiny little refactorings that you continue to execute in every sprint throughout many weeks behind the scenes. You never, ever go to your boss and say, we need 2 weeks to refactor. Don't ever do that. Right? That's not their business. That's your business. You take care of your business behind the scenes all the time.
Behind the scenes. That's good.
Yeah.
Another tough one. If you could go back in time, what would you try to change in the way we do software development that would fundamentally change the way we do it today?
Wow, what an interesting question that is. Something happened in 1975-ish, maybe a little before, maybe a little after. And what happened was that the demographics of programmers shifted dramatically. Prior to that time, programmers were in their 30s, 40s, and 50s, and about half and half men and women. After that moment, and it was a very sharp moment, programmers were almost entirely in their early 20s and boys. I don't understand why that happened. There's been books written about this. There's been lots of discussion. Some of that discussion is acrimonious. It's not a pleasant topic to discuss. But something happened in the mid-70s that caused this demographic shift. And if I could go back in time to the 1970s and change the hiring practices of companies, I would do that.
I remember you saying that every 50 years, the number of developers is doubling, something like
Every
that.
5 years.
Exactly.
Every 5 years.
Every 5 years. Is this law still correct?
Oh, is it still correct? It's hard to know if it's still correct. It's pretty easy to track the last 2 decades. And the last 2 decades have shown about a doubling every 5 years. And you can go on Stack Exchange and look at the number of people on there and the age demographics. It's very simple to plot that curve. Is it still happening? Well, it's always hard to know today if that rate is still going. But there are hints. Notice how in the midst of this pandemic, the software community is still vital. It's still active. We're having conferences. We talk to each other. I mean, we as programmers are not hugely affected by a pandemic that is sweeping the world. And that is because A, it's easier to work from home as a programmer, and B, programmers are vitally necessary to our civilization. So that's a hint. That's a clue that maybe we are still doubling at that rate. I do expect that doubling rate to slow down because it must. There are only 8 billion people on the planet. It doesn't take long to get to 8 billion if you're doubling every 5 years. So I do expect that rate to slow down, and I hope it slows down soon.
Okay, the last one. The last question, because our time is up. Can MVC still be saved? How would you do it?
Oh, I don't think it needs saving. I don't think Model View Controller is at any risk at all. The original view of Model View Controller is still a very powerful design pattern. I would follow that without any thought. That's perfectly fine. The implementation of Model View Controller that was used in early websites, I think, needs to be modified. Although there are good modifications to it. The Model View Presenter idea works very well. The MVVM system works very well. You know, the Microsoft View Model notion, that works very well. For websites using some kind of model view presenter controller kind of design pattern, I think that's fine. Design patterns are truths. They are not fads. They don't apply at one time in history and then not at another time in history. Model View Controller is a good design pattern for the purpose that it was designed for. And that will remain true forever.
Unfortunately, our time is up. Mr. Martin, thank you so much for joining us today.
You're very welcome.
Ovidiu, please.
Robert, thank you very much. It was a nice pleasure to have you as a speaker, and we are looking forward to meet you again.
In person.
Hopefully.
In person, maybe. I mean, a lot of person here in Cluj were asking, hey, is Uncle Bob coming here in Cluj? We want to see him. So I say, okay, he cannot come even if he wants. So, but next year, if you got over this pandemic stuff, will be great to have you here. Thank you very much, Robert. Thank you. And we got a lot of interesting questions today. We couldn't ask you all of them. Thank you for our viewers about them. We'll try to respond. Maybe we'll see, but we'll keep those questions. I can forward an email to you with all those questions. Are pretty interesting.
Okay.
Okay. Thank you very much. And with this, we are ending this evening. Thank you, Robert. Have your coffee now.
Have a nice day.
Yeah.
Bye.
Thank you very much. Bye. Thank you.